Chapter 14, Section 3, Analyzing the Performance of the Selection Sort Algorithm. I remember selection sort from the preceding part of the chapter deals with sorting an array, in this case of integers, in ascending order. The way this works is it checks the first element, scrolls all the way through, all the remaining elements, finds if there's a smaller element. If so, it swaps them. Then it goes increments the index 1 up, starts there, that's the new smallest, search the array, is there a smaller one? If so, swap them, and it goes all the way through. So a fairly simple array to sort of read and understand, and a rather simple array to implement, but as we found out, it's a quadratic as far as its efficiency. So we're going to look into actually how do we determine sort of the efficiency of an algorithm, and this sort of notation, this sort of concept will come up on the AP exam, so it's something that you should be at least familiar with. So to analyze the performance, obviously beforehand, the other day in class, we did come up with the chart of milliseconds of how long it took. And again, on page 634 in your book, an array of 10,000 items on that computer took 786 milliseconds, or 0.786 seconds, all the way through an array of 60,000 elements, which took 19,299 seconds, or milliseconds, that is 19 seconds on that old computer in which they wrote the book. So not particularly efficient if we're starting to deal with hundreds of thousands or millions of items long. Every time you double the array size, you essentially quadruple the time it takes to run it. So how do we come up with sort of the efficiency and the notation? Well, obviously you can't really come up with how many steps it actually takes the computer to do something. So instead what we'll do is we'll just sort of look at how many times does an array element have to get visited to sort this thing up. So if you're going to have n, it's going to be your sort of italicized lowercase n, is going to be the symbol for it. That's going to be the size of the array. So first thing that has to do is it has to find the smallest of all of the array elements. Okay, so you have to visit every element in the array. Then you swap the elements, which is 2 more visits. We're not going to worry about getting an efficiency of sort of if we don't have to swap them. And then after that, it's n minus 1 elements to find the minimum. Okay, then n minus 2, etc., etc. So we sort of get this the first time through, it's n, visit all the elements, plus 2 times the swap. That's the first sequence. Then the next time it takes n minus 1 times, plus the 2 to swap, etc., etc., all the way till we get to the end. So you can simplify this into the following. Okay, so we can get it down to there, and if you were to expand that out, we end up with 1/2 n squared plus 5/2 n minus 3. So sort of saying for any given array size n, it's going to take that many steps to sort this entire array. Well, how does that actually matter or sort of come about? So if we start going really large values for n, so 1,000 or 2,000, then we're starting to talk the 1/2 n squared is 500,000 or up to 2 million. All right, the lower term, the 5/2 n minus 3, isn't nearly so big. So my 1/2 n squared, if n were going to be 2,000, then this comes up to be 2 million items. The other half, the 5/2 n minus 3 part, that comes out to be 4,997. So this part here doesn't really affect the other part too much. I mean, when we're comparing 2 million, what's another 5,000? So we're going to drop that whole thing. We're only going to take the first term, and that's the only one you're really going to care about. So we got our 1/2 n squared, okay? And we're even going to drop the constant. Anytime you see a constant, we're going to kick that out because we want to compare the ratio of counts for different values of n. All right? So if I was to say 1/2 times 2,000 squared and 1/2 times 1,000 squared, I get a ratio of 4. So doubling my array size takes 4 times as long. So we're also going to scratch out the coefficient part. And what's left is going to be what we say is our sort of efficiency, our very simplified efficiency for this algorithm. So n squared, so quadratic, which when we looked at the plot and the graph which is on page 634, it did in fact look sort of like a quadratic or a parabola, right? And which makes sense, because that's what we just figured out. N squared would in fact be a quadratic curve. All right, and then to indicate this, we use what we're going to call big O notation. All right, so if you see the term big O notation, okay, and that is the number of visits. So the function would be f of n equals O g of n. Means that the function f grows no faster than g, or that for all n larger values from threshold, the value of f of n divided by g of n is greater than or less than or equal to c for some constant c. Okay, and the way you're going to see this generally written is just O of n squared. That would be the big O notation for this problem, or the efficiency of the selection sort algorithm.